Hi, good afternoon, everyone. Thank you, Academic of Sciences Malaysia, for inviting me as a speaker of this FAScinate session. Today, I'll be talking about biodiversity and how remote sensing technology can be used to monitor changes in biodiversity and why we need to monitor these changes. I will cover the following topics. First, I will start by providing a brief overview of biodiversity, and then I will focus on remote sensing for biodiversity monitoring components. Finally, I will share 2 case studies conducted in Malaysia before I conclude my talk. First of all, let me explain to you what biodiversity is. Biological diversity, or in short, biodiversity, is a term describing the variety of life on Earth at all scales ranging from genes to species to ecosystems. It encapsulates the structure, function, distribution, traits, and composition of all living things such as plants, animals, including humans, and microorganisms such as bacteria and fungi. The figure here in this slide shows the statistics of biodiversity in Malaysia as of 2015. A total of more than 174,000 types of lives have been identified, and majority of them constitute invertebrate class. All of the Earth's species work together to survive and maintain their ecosystems. Many species provide important benefits to humans, including food, shelter, clothing, clean air, clean water, and medicine. Unfortunately, we are losing global biodiversity at an alarming rate. Approximately 11,000 to 58,000 species are being lost annually. The current rates of extinction are about 1,000 times the natural rates of extinction, and there has been an overall decline of 69% in the wildlife population size between 1970 and 2018. And the greatest overall global decline occurred in freshwater species populations. Biodiversity loss is an urgent and systemic environmental risk as it impacts the global food security, public health, and the resilience of natural life. Key indicators of global biodiversity loss are the declining extent of forests, reduced coverage of protected areas, dropping of the Living Planet Index. It is challenging to observe and monitor biodiversity as human activities are changing the structure and composition of living organisms. Land use change, pollution, climate change, and population growth are all threats to biodiversity. Since 1992, the Convention on Biological Diversity has pushed the effort to stop or at least lower the accelerated loss of biodiversity. But indeed, it remains one of the key global challenges, and it requires an effective use of modern technology. The Sustainable Development Goal 15 on the Agenda 2030 is devoted to protect, restore, and promote sustainable use of terrestrial ecosystems and stop biodiversity loss. Other global efforts include the Aichi Biodiversity Targets, IPBES, the post-2020 negotiations of the CBD. Tracking biodiversity change is increasingly important in sustaining ecosystems and eventually human well-being. Initial efforts to collect data about different species of animals and plants and the impact of land use change on them in a particular area was conducted by taxonomists through field survey. Field surveys are organized in plot units, which represent a small area from which general conclusions about the overall environmental conditions are drawn. But biodiversity assessment needs multi-temporal data acquisition across local to global scales. Remote sensing is the best tool available for coping with this challenge, and I will now briefly explain what remote sensing is. Remote sensing can be broadly defined as the science of obtaining information about objects on the earth from a distance using instruments such as camera and sensors mounted on aircraft or satellites. Remote sensing system consists of data acquisition and data analysis, as you can see here in this slide. Data acquisition involves detection and recording of electromagnetic radiation, where electronic sensors convert electromagnetic radiation into electronic signals that can be stored as digital images. Remote sensors can be either passive or active. Passive sensors record natural energy from the sun that is reflected or emitted from the Earth's surface. In contrast, active sensors such as microwave and laser emit their own source of energy onto the Earth's surface and collect the amount of radiation backscattered by them. The reflected and or emitted signals are unique to every Earth's surface features, and images capturing such differences contain much information on the nature of the Earth's surface. Data captured by the sensors are sent to the ground receiving stations where they are processed and distributed to users for further interpretations. The final product is usually a map showing the spatial distribution of the variables of interest. Maps generated from remotely sensed data can be used directly or in combination with other data sources such as field survey for a variety of applications, including mapping and monitoring patterns of biodiversity across large spatial extents. The space-based satellite data are advantageous for biodiversity information due to their synoptic view that cover large area at regional and global scales and repetitive coverage of several days to several times in a day with less cost. Measuring biodiversity means not only reporting the types of species, but it also covers many other biodiversity relevant measures, including measures of change in ecosystem structure and function, community composition, species traits, and species populations as shown in this figure. However, it should be noted that some biodiversity measures such as genetic composition is not measurable from space for now. To support biodiversity monitoring systems, the Group on Earth Observations Biodiversity Observation Network, GeoBond, developed the concept of essential biodiversity variables that can be regularly monitored from space. For today's talk, I will focus on two essential biodiversity classes, ecosystem function and ecosystem structure, where remote sensing can contribute to measure these variables. And in the next section, I want to share two case studies that my research team and I conducted in Malaysia that demonstrate the application of remote sensing technology for biodiversity monitoring. Okay, in the first case study, I want to show how remote sensing technology can be used for monitoring ecosystem functioning. In this study, we detected mangrove cover loss and fragmentation in Iskandar, Malaysia, in the south of Johor. I'm sure all of you are familiar with mangroves. If not, the pictures on this slide should provide a glimpse of mangrove forests in Tanjung Piai, Johor. My research team is in action collecting some samples here. Mangroves are actually shrubs and trees of medium height, grow in many subtropical and tropical areas of the world, including Malaysia, as you can see in the global map on this slide. For your information, the map was produced using an active remote sensing system. Mangroves grow along sheltered coastlines, and in Malaysia, they are found in the west coast of Peninsular Malaysia, Sabah and Sarawak. The total global coverage of mangrove was 14.73 million hectare in 2020, and this is only less than 0.4% of the world's forests. Although they cover only a fraction of the Earth's surface, mangroves play important roles in providing habitats for thousands of marine and pelagic species and serving the local communities with food, medicine, fuel, and building materials. They also become important in mitigating the impact of climate change by accumulating carbon dioxide from the atmosphere and protecting the coastal areas from tidal waves, tsunamis, and cyclones. Despite their significance in providing ecological and economic services, mangroves are being lost globally with a net loss of 3.4% between 1996 and 2020. The loss rate is approximately 2 times higher than their gain. The rate of loss is highest in developing countries, and in Malaysia, the rate is estimated to be about 1,290 hectares per year since 1990. Generally, mangroves are cleared for coastal development, aquaculture, timber, and fuel production. As I mentioned earlier, the first case study was in Iskandar, Malaysia. And Iskandar, Malaysia is a fast-growing national special economic region with a total area of 2,200 kilometers square located at the southern part of Johor. 3 of the 7 Ramsar sites in Malaysia, namely Pulau Kukup, Tanjung Piai, and Sungai Pulai, are found in this region. In this study, we used passive remote sensing imageries. If you still remember, I explained what passive remote sensing is in the previous slide. We used passive remote sensing imageries from Landsat and Sentinel-2 satellites to monitor changes in mangrove cover and fragmentation between 2000 and 2019. The use of the machine learning technique to classify the Landsat and Sentinel imageries showed great capability by clearly distinguishing mangroves from forests and water bodies, which often can be easily misclassified. From the classification results, the loss of mangrove area is noticeable, particularly where it has been converted to urban area and oil palm plantations. We found an expansion of the urban area, especially at the eastern part of Sungai Pulai, where the new Nusa Jaya township is located. And in the central part of Iskandar, Malaysia, where Kulai Senai township has expanded due to increased population. Interestingly, the conversion of mangrove to aquaculture land use was found at multiple locations, as you can see here, which showed the recent development and expansion of the economically valuable aquaculture activities in the region. A net loss of 2,900 hectares of mangrove has occurred in Iskandar, Malaysia over the last 19 years. This is equal to 1.1% of annual mangrove loss in the region, which is higher than Malaysia's mean depletion rate of 0.4%. The southwestern part of Iskandar, Malaysia, as you can see on the far left image, where the Ramsar sites, Pulau Kukup, Tanjung Piai, and Sungai Pulai mangroves are located, these areas faced significant loss over the study period. On the other hand, the eastern side of Iskandar, Malaysia, this part here, new patches of mangroves were noticed. The new mangrove areas which were noticed in the 2019 image are marked in blue color. Okay, now let me talk about fragmentation. What fragmentation is? Fragmentation is the subdivision of a continuous landscape into smaller units which can be characterized based on patch size, edge, and shape modification. Fragmentation can affect ecosystem habitats, species number and diversity, and carbon storage capacity. Based on all the fragmentation indices as listed here, a reduction of the total landscape area of approximately 3,000 hectares can decrease the movement zone of animals and discourage flora and fauna succession within or between fragments. An increased number of patches from 130 to 402 in 2019 and decreased mean patch size from 105 to just 27 hectare means increasingly isolated mangrove patches lead to a loss of connectivity between patches. For example, in Sungai Pulai mangrove area, one large patch in 2000 was fragmented into 60 smaller patches in 2019. This can prolong the migration of animals to surrounding habitats due to the decreased existing habitat size, which can stimulate species extinction. Malaysia has the highest reduction of mangrove mean patch size, ranked at first place in the nations of the world as reported in the global scale study by Brian Brown in 2020. The age and shape indices reveal that human-induced disturbance is significantly influencing the mangrove forest. The decreased mean shape index value from 2.8 to 1.9 show a reduction of shape complexity, which could be due to the transformation of mangrove areas, which is irregular shaped into regularly shaped or spaced patches of urban, agricultural and aquaculture uses. The changes of edge and shape complexity could ease human access to the fragmented patches and exploit the remaining mangrove forests. This could accelerate the loss and fragmentation of mangrove areas in the future. Satellite imageries combined with geographical information system analysis greatly assist us to understand fragmentation and its impact on biodiversity without having to spend tremendous amount of time, energy and cost collecting data in the field. Now, we need to strategize how to use this precious information from remote sensing to conserve the entire mangrove area in Malaysia. Okay, now let's move from the south to the north of Johor to the district of Segamat. In the second case study, I want to show you the use of remote sensing to detect forest cover loss and identify the drivers of deforestation. In this study, my research team combined both the remote sensing technology and social survey methods. As I mentioned earlier, forest extent is a key indicator of global biodiversity. To monitor the status of biodiversity, changes to biodiversity, and the effects of management actions. Similar to mangroves, forests also provide multiple ecosystem services and contains a large proportion of the Earth's terrestrial biodiversity, including birds, vertebrates, invertebrates, microbes, and also indigenous human community. So, we wanted to understand the changes occurred in the forest extent, its drivers and impacts to an important component of the forest, which is the indigenous community living in the district of Segamat. The map here shows the boundary of Segamat district, which is shown in blue, and the red box refers to one of the forested regions that is suspected to undergone deforestation. The boundary denoted in yellow polygon is the Endau Rompin National Park, a protected area. Since the area of interest lies close to the protected area, we were also interested to know if any forest cover loss occurred within the area. For the purpose of this study, 8 villages, namely Segamat Kecil, Ulu Juase, Seri Tempayan, Kudong, Tamuk, Kemidak, Selai, and Lenek were selected to understand the impact of deforestation on the people's livelihood. In this work, we used an active remote sensor that emits its own microwave energy to detect features on the Earth. The advanced land observation satellite called ALOS 1 and ALOS 2 were launched by the Japan Aerospace Exploration Agency JAXA in 2006 and 2014 respectively. Generally, the average backscattered microwave values in these data enabled us to differentiate and discriminate forests from other land uses such as oil palm and water. Analysis of the satellite data shows that a total of 2,500 hectares of forest cover change occurred between 2010 and 2017 up to 5 kilometer radius from the Orang Asli villages. In this slide, I want to show the oil palm expansion work done by Denny Law in 2021. They used Landsat satellite images to detect changes that occurred in oil palm plantations worldwide from 1983 to 2019. This data clearly shows that oil palm expansion occurred within the study area. Most interestingly, oil palm extension is also spotted within the protected National Park of Andau-Rompin, which is shown in the next slide. If you look at this zoomed in picture, you will notice oil palm expansion occurred from mid-90s until recent days and expansion into the national park. This is further confirmed by another recent publication where the same ALOS pulsar data was classified using a machine learning technique to detect oil palm extent. We produced annual oil palm plantation maps in 4 major producer countries, Indonesia, Malaysia, Thailand, and Papua New Guinea, at 100-meter resolution. We uncover the global patterns of oil palm expansion and find that global oil palm expansion has a very high degree of potential conflict with local biodiversity. Globally, 99% of oil palm plantations overlapped with conservation priority zones, and oil palm plantations encroached on 231 protected areas. Based on the satellite data analysis, we confirmed that oil palm expansion could be one of the reasons for the forest loss within the indigenous peoples' villages. But who are responsible for this? I will now present the answer based on information that we collected from focus group discussions, interviews with local forest officers, and through a questionnaire survey with 200 indigenous people from the 8 villages. The forest cover loss map that was produced using satellite data, this map, was very helpful in the discussion with the villages. Based on the survey and focus group discussions, it was found that deforestation is occurring until a month from our interview date, and the reasons are 38% of the villages stated that it was for small-scale agricultural purposes such as planting oil palm, rubber, and fruit trees. Another 34% of the villages stated that forest cover loss was due to illegal logging, especially near Andau-Rompin National Park, by unknown sources, and a further 28% of the respondents thought that other factors such as cutting trees for woods for local use, development projects such as railway and housing by the government, and land erosion may contribute to forest loss. These reasons were further confirmed by the attendees of the focus group discussion. The villagers informed that one family could clear approximately up to 20 acres, and they consider the clearance as legal as they do not transport the logs outside the villages or selling them. It was surprising to learn that as large as 600 acres of forest have been cleared in and around some villages. According to the forestry officer of North Johor Forestry Department, indigenous people or Orang Asli may be clearing the forest for planting crops to increase their daily income. He also thinks that outsiders may use the local people to cut down trees, or the local people seek assistance from outsiders to clear the forest and allow them to take the logs as a payment for clearing the forest. These photos were taken during our visit to the villages. We can see clearly how oil palm has extended into the forest at the villages' backyard. The impact of deforestation on the environment is obvious, where 41 to 47% of the people interviewed agreed that deforestation affected the supply of clean and fresh air, health of the villages, and food supply chain. They also agreed that deforestation reduced the availability of public space for recreational activities and relaxation. A large proportion of people strongly agreed that deforestation caused loss of fuel wood and environmental disasters such as soil erosion and water pollution, although the impacts may vary from one village to the other. Generally, the respondents feel that there are negative environmental impacts due to deforestation in their area. Reduced coverage of forest areas has become a threat for wild animals like elephants in Sungai Lenik village, as they have lost their habitat. These photos were taken during our visit to the villages, showing shallow river and resulting flood or waterlogging and land erosion in the villages. The second case study demonstrated the use of remote sensing technology to monitor forest loss and to assess its impact on people's livelihood that depend on a sustainable forest use. Okay, finally, I want to conclude my talk by emphasizing that biodiversity monitoring is important because biodiversity is a marker of ecosystem stability. Mangroves and inland forests are rich in biodiversity, thus any changes to the coverage of the ecosystems will affect their services and disrupt the functioning of the whole ecosystem. Unfortunately, we are losing these ecosystems at an alarming rate. Monitoring and detecting the loss are urgently required for identifying key issues for policy and management goals, assessing priorities for conservation, and informing policymakers and the general public on the state of biodiversity. But monitoring continuously covering large areas are impossible by field survey alone. Alternatively, we have technology that can acquire enormous amount of digital data on a continuous manner for assessing biodiversity condition and its loss over time. Monitoring should not be an end in itself, but a means to an end. The aim of biodiversity monitoring should be to provide guidelines for making decisions on how to best manage the landscape for the production of resources for the human population and at the same time to maintain biological diversity. I really hope we can develop a remote sensing based monitoring system to conserve biodiversity in Malaysia. Thank you very much.